Transdermal drug delivery is an interesting mechanism of delivering drugs to your body. It can be done through a patch, like a nicotine patch some of us used to wear, or through a cream, or potentially other applications. Now, skin is an excellent barrier for drugs, so even small molecules find it hard to get through the skin. So today I'd like to take a look at the paper where electric discharge, called plasma, is used for transdermal drug delivery. Let's take a look. So here we have a recent publication from January 21st, 2020 in Skin Pharmacology and Physiology on plasma permeabilization of human skin. And what's interesting about this paper is they compare two different plasmas. Very popular recently nanosecond pulsed plasmas to microsecond pulsed plasmas. Now what they're doing, so if you Google image search DBD plasma on skin, you'll find these pictures like the finger being treated here, or this electrode. So this is plasma that's generated directly on the skin. And I found a very nice video from YouTube, which I will link down below. This is what your finger sees. So this is, in this case, a transparent electrode is serving as your finger. So this is what plasma is generated directly on the surface of your finger, much like in many of these photos. Like, for example, here we see skin and the plasma on top of it. Now what they do, they take skin from human patients, they put it on something called Franz cell, where skin would be right here. They will add a fluorescent molecule and then measure diffusion of fluorescent molecule from here through liquid, through the skin, into the fluid over here. And the fluorescent molecule they're using is sodium fluorescein, which is a relatively small molecule. And so getting back to the paper, their primary goal is transdermal drug delivery, as we discussed. They're trying to deliver small and hopefully even large molecules through the skin. Key finding in this paper is they compare different plasmas that are very, very common. They're called dielectric barrier discharges, and they're comparing nanosecond one with a microsecond one. Plasma is well known. It's been applied widely for skin treatments without any extensive tissue damage, heating, or burning, as is also indicated below in this paper. They take the electrode, and much like in the images that I showed you over here, they're applying plasma directly to the skin sample in this case. And then they put the skin sample in the Franz cell and measure voltage across and diffusion of fluorescein into. This has been observed previously, for example, with fluorescently labeled dextrin molecules, and with other things like my favorite is vitamin D for the seasonal disorder, that you can use vitamin D, mix it with any kind of cream, and just apply it to your face for vitamin D delivery. And dielectric barrier discharges have been well known for treatment of skin. They generate a lot of reactive species, which we can go into detail in maybe some other videos. The human skin samples they used are from patients, basically they're discarded samples from patients undergoing various plastic surgeries. It's a very nice source of skin, and it's putting otherwise trash into a very productive, very good scientific use. Their specific electrode is a copper electrode that's 8 millimeters diameter, so about the size of your finger that they're using to treat skin. It's an interesting solution, and they're keeping this finger about 1 millimeter away from the surface. Now they're applying two treatments, 90 seconds each, with a 10-minute interval to let the skin cool down. They're using microsecond pulsar with 300 hertz pulse rate right here, and then power of roughly 300 milliwatt per square centimeter, 600 milliwatt per square centimeter for high power, and they're comparing it with a nanosecond pulsar with roughly 300 milliwatts, so comparable with low power. The microsecond pulsar at low power is 1 microsecond pulse width versus 5 microsecond pulse width at high power versus 28 nanoseconds pulse width for the nanosecond pulse DBD. And you can observe the waveforms here, but they're not that important. Now, what's interesting is if you look at conductivity of the skin, as you're increasing skin permeabilization, its conductivity should decrease. And they see decrease in conductivity for microsecond pulsar and for high power microsecond pulsar, but not as much for the nanosecond pulsar. By the way, something interesting to point out, here is A, here is B, here is C, and there is no C here, which is, we all make mistakes, even in published and peer-reviewed literature. But anyway, I digress. So they look at permeated sodium fluorescein. Higher number would be more permeation, and they look at it over time. So 30 minutes after treatment for control, nanosecond and microsecond pulsar, there is not much penetration observed 30 minutes after. Not much observed in 2 hours. However, in 12 and 24 hours, we see pretty significant increase in permeabilization, especially for the high power microsecond pulsar, which one would expect. You're making more holes in the skin. What is a little bit surprising is nanosecond, while comparable power to low power microsecond, there is pretty significant difference in permeabilization of skin. Then they also measure peroxide and nitrate on the skin and do some thermal observation. Peroxide, as one would expect, nanosecond pulsars produce higher concentration of peroxide. Many scientists have reported this. What's interesting, however, is low power and high power microsecond both generate less, that's expected, but about as much. So we don't have much chemical difference on the skin there. Similar with nitrate, not much difference between low power and high power microsecond. However, with nanosecond, I would expect to see a little bit more, but I don't. Well, that's okay. Infrared skin images look as expected. So nanosecond, you're looking here on this side, you're looking at image during treatment, and on this side, you're looking at the image as fast as they could image it after the treatment. So they're claiming a couple of seconds after the treatment. So they treat, and we observe temperatures of maybe around 30 Celsius temperature of the electrode. It doesn't really heat up that much, and we see a little bit of warming on the skin after nanosecond. Low power microsecond, about the same heating of the electrode, similar temperature, maybe in the upper 20s on the skin. So this is pretty much room temperature. It depends on which room you're in and what time of the year, but it's close to room temperature. And with a high power DBD, as one would expect, there is much higher heating into mid 30s. And there is, pretty significant heating. Keep in mind that this is 90 seconds that they're treating the skin for. What they observe is both nanosecond and microsecond pulse dielectric barrier discharges were capable of creating pores in the skin, which is nice observation. The most interesting observation of this paper is lack of difference between relatively expensive and relatively complicated nanosecond pulsars and low cost, easy to generate microsecond pulsars. So hopefully this will lead to further research in this direction and further commercialization. And I applaud the authors on this excellent work and hope they continue to do more of it. Thank you.